let's go for chapter 5 for shaft in a way. That what we experience on chapter 4 is already on the shaft design, things like that. That what we find difficulties when we just design the shaft, things like that, for some kind like the shaft due to rotating shaft, things like that. Because that's why the shaft is going to be the major components that what we just take it from the prime mover anyway for some kind like a pump, like a utensil, things like that, that what we used for a long time, things like that. So therefore, basically, we need this necessity to design this kind of shaft in this chapter 5. So the ASME just use some kind of easy manner to design a shaft, only one single equation can solve all the problem, things like that, with only one single equation of the design, things like that. Okay, so therefore it's gonna be easy for the easy manner to design this kind of shaft anyway. First thing first, for the section 1, for the standard shaft diameters anyway, what typically the ISO is choose International Standards Organization that's based on the ISO anyway, that what issue that what the basic manners on the shaft diameters is available. It's gonna be the things that was appears on the table 5.1 respectively. So therefore, the selection of the shaft nowadays that what we just make a selection based upon this type of diameters anyway. That you got to be careful anyway because that's why the size of the shaft diameter is going to be according with the bearing and the many size of the corresponding shaft associated shafts anyway, like some kind of pulley in the size of the diameters of the pulley, whatever, things like that, and also the associated bearings, things like that. What we study, we're going to study about it in the same manners anyway. Then what table 5.1 show the nominal shaft diameters anyway. That what I show you on this is going to be nominal. It means we can take a measurement on the exact shaft diameter that what manipulate on the shaft diameters anyway. See? So this kind of thing is kind of the basic thing that what disappears on it. And then the shaft design based upon the ASME code anyway, the American Society of Mechanical Engineers just realized about the necessity of design of the shaft, things like that. It's been issued in the year 1954. That what basically the shaft is gonna be basically on the torque and on the bending, things like that. So therefore, the SM realized about this necessity and issue the fatigue factors and everything's on its own design, things like that. So just issue only one single equation that's going to be able to apply for all anyway, for the hollow shaft and the solid shaft, things like that. We can use only single equation to apply it on it. The cube equal to 16 of pi tau in the parenthesis 1 minus k to the power of 4, things like that, c t t square and plus whatever under the square root whatever, where d is the outside diameter, d is our pi equal to inside diameter, and t the maximum. So the SME just consider only for the maximum torque only, and m is going to be maximum bending moments only, and k is going to be the ratio of the inside diameter over the outside diameter, things like that. And then the tau is allowable shear stress, and ct and cm is got fatigue factor due to the torque and due to the bending moment respectively. And then for the solid shaft, d sub I over t is going to be 0. So therefore, the corresponding ASME code is going to be able to just make modification to be the equation here. So for the solid shaft. And for the keyways, so therefore for the keyway, just the accordance ASME just make some kind of like adjustment for the tau desired to be recommended to be tau desired equal to 0.3 times sigma y, and tau desired equal to 0.18 times sigma u. Choose the smallest magnitude to be able to use for those corresponding equation. Okay, and for the shaft with keys, of course, they realize about the stress concentration factor. They just make a reduction of 25%. So therefore, they just time it up by 0.575 percent for seven, so I'm sorry, 0.75 to the corresponding equation, then use the smallest magnitude, okay, and then apply for the ASME codes, things like that. And then just for the ASME code anyway, for the tile design, for the general cases anyway, for the normal matches of the chaff anyway, this was for the keyway. Without the keyway, use the tile design of 55 and tile design of 41, things like that. But this is for the standard things that what the shop just want be able to employ in the developed country anyway. See, for the underdeveloped and developing country, we're not allowed to do so anyway. See, we gotta be careful anyway. In Thailand, we're not allowed to do like this anyway. Okay? So therefore, this is going to be very sensitive value for the fatigue factor CM and CT respectively. For the stationary shaft, this is going to be some kind of structure, okay? Structure component. See, for the stationary shaft, it means it's going to be a structure one. Uniform loading or increase uniformly is CM and CT is one. Less corresponding is one respectively. Fluctuating loading is 1, 2, 2. For the rotating shaft for uniform or increase uniformly 1.5 and 1. And fluctuating loading 1.5 and 2, 1 to 1.5. For the sudden or fluctuating loading or severe loading, things like that, it's going to be up to 3, things like that. Okay, another one that what we talked on chapter 1 already, angle of twist. Say that is equal to torque times L over G times J is corresponding J is in terms of table 1.2 in chapter 1 respectively. And another one is critical speed based on the mechanical vibration. See, based on the road for the natural critical speed for natural vibration that we got to stay away from it. And sub C can be defined from this equation. N sub C for the critical speed on the RPM. W is the weight applied on the shaft, and what is deflection of the shaft respectively. T, the W is going to be corresponding weight of the W1, W2, and W3 respectively. So therefore, the equation is going to be look like that. Okay, and the AK equation is going to be substitute in the corresponding manner, look like that. So we have an example. Have a quick look at it. A solid shell without a keyway uses tons of power up to 110 kilowatts at a speed of 1,800. Its transmission is quite uniform, acting manners, given that these shafts of steel have a sigma wide of more than 90 determine the shaft diameters. Okay, so the power can determine from the 2 pi n times t, and then we find the torque in terms Newton meter. I mean a millimeter, things like that. Okay, so therefore we plug in the ASME code, and CM and CT just from table 5.2 is going to be uniformly, so therefore it's 1 and 1.5 respectively, and then we plug it in the corresponding manner without moment, bending moment, so therefore the tau is going to be 0.3, so without any keyway, so therefore we just plug it in. We have a diameter of 37. We have lookup in the table 5.1. Come closer for the consequences. Sharp diameter, we make a selection of 40 millimeter we will use anyway. Okay, and say example 5.2 from of the power, things like that. We're gonna have a look at it. Maybe you have a look at it by yourself, things like that. 5.3, okay, you have the examination on the critical speed. You have a look at it by yourself, please. Okay, very clear on it. Okay. All right, so let's have a look at another example that what we've got there. Okay, that what we have done on chapter 4 already. The same exactly the same example there. We said the solid shaft as shown below, mounted on the key on the pulley with keys, profile, keyway. So therefore, KT and KTS is going to be 1.6 and 2 respectively. And then, as the method of AISI 02CD steel. So we just design the shaft diameter by the method A is going to be Soderberg method, and B is ASME code. Okay, in A that we have done on it already in example in chapter 4, and then in B that we're going to use ASME, okay, that what we have it already in A. See, we got the diameter of 43.84. So therefore, when you make a selection for the consequences table 5.1, we got 45 millimeter as the table available there in table 5.1. And then let's see the math of ASME very short there, and then see we made of steel, right? So therefore we got of 1020 CD steel, we got sigma Y and sigma U respectively. Of course we have a keyway, so therefore we have a tau design of 87.75, tau design of 63.45, and then therefore we have got the smallest one. So if I make a selection of 63.45, and then we just got for the moment max and the torque max. See, be careful here. See, the ASME consider only on the maximum moment and torque. Okay, maximum only. See, they don't care about the point of stress concentration at all. And then see from the table 5.2, based on this problem set, haven't said anything about the type of loading, whatever. And we just consider for the very uh, normal condition, things like that. So that's why we just assumes to be uniform loading. CMC is T is going to be 1.5 and CT is 1. So that's why we plug it in the SFME code. So we got the diameters of 33.65. So therefore, if we compare the two method together, okay, so therefore the answer is different. So then what I mentioned earlier, CM and CT is gonna be the things that what make us the difference in answer anyway, because that's why CM and CT is gonna be some kind like a sensitive value anyway. So if you just change the values to be CM and CT at 3 and put for the calculation, you may achieve the same answer anyway. See, so this is, you may try it out by your own anyway. See, so this is the things that what you might use both of them anyway. See, so okay, these are the things that what you may try it on it. Okay, we have a problem set 1, 2, 3, and 4, things like that. Okay, and then we have another example on 5, 6, 7. Okay, 8. Okay, and 9, things like that. Okay, I would like you guys to do on problem set number 9. Okay, please try it and sub it to me. Okay, on problem set number 9. Okay, as a homework for me. Okay. All right, so this is gonna be it for chapter 5 anyway. Okay.